right. Hi, everyone. I am super excited and happy to be here. This is another episode of Platformers. And my name is May. I am a platform engineer at Forter. And today we're going to talk about GPUs in Kubernetes, past, present, and future. And we have Kevin to do this for us, to talk with Kevin about it. Kevin, why don't you go ahead and present yourself to our dear audience, and then we
Sure.
can start.
Yeah, sounds good. Yeah, thanks again for having me. I'm really excited to be here. My name is Kevin Klues. I'm a distinguished engineer at Nvidia, and I lead the team at Nvidia that enables GPU support inside containers and Kubernetes. I'm going to be talking today a bit, as May said, about kind of the history behind how GPU support was initially added into Kubernetes, what it looks like today, how it's developed over time, and where we're looking to go in the future with kind of some of the more advanced features that we're building into Kubernetes today to enable more advanced use cases with GPUs.
So I'm excited already because I think that this is one of the topics that it's not something that is very common in at least my day to day. So I'm always super hyped in hearing about more things that are possible in Kubernetes. One more thing for that I want to say to our audience here is that you're all welcome to ask questions. The more, the merrier. Just write them in the comments, and then when we will do the Q&A breaks during the talk, then I will read those questions and Kevin will happily answer them. And I think that's it. In my opinion, now would be the perfect time for you to start your session. So Kevin, go ahead
Okay,
and
thank you so
begin.
much. Okay, so as I mentioned before, title of my talk is GPU support in Kubernetes, past, present, and future. So I assume most of you on this call are probably familiar if you're here with what Kubernetes is, but I figured I'd give just a really quick, brief overview of what it is for those that aren't quite as familiar. Kubernetes is what we call a container orchestrator, which means that it's able to manage groups of what we call containers that are organized into something called pods across a cluster of machines. It was informed and inspired by Google's experience with their internal systems, and it's a 100% open source system for doing this, right? So you can take your software, you can package them into these containers, you can use pods to then orchestrate them across different machines in your cluster. Um, and given that we're talking about, uh, orchestrating these containers across a set of machines, and we're talking about how to actually enable GPU support in these environments. I first want to talk about what some of the challenges are with supporting GPUs and containers in general. Independent of Kubernetes, what does it take for us to actually support GPUs in these environments? Um, well, if we look back before containers existed, um, it was somewhat more straightforward, right? You could buy some GPUs, you could install them on your box with some kernel. You can install the Nvidia driver, which included some kernel level component as well as some user space component in terms of Nvidia driver libraries. You could then install some advanced toolkit libraries on top of this, whether it's CUDA and TensorFlow libraries that you might want to use to enable your workloads. Actually install the application itself, you link it against these libraries, and then you run your application. And all of that is installed directly on the host rather than inside of a container. So what about containers? The beginning of this process is the same, right? You buy some GPUs, then you install them on your box, you install the NVIDIA driver, and then ideally what you'd be able to do is just take a container that bundled your NVIDIA driver libraries, bundle your advanced toolkit libraries, and bundle your GPU accelerated application inside it, and then move from machine to machine and expect that it runs, right? Because that's what containers are meant to do. They're supposed to bundle all of these user space things and make it easy for you to run on whatever machine you have available in your environment. Um, and then run your container, obviously. Um, Problem is, this will only actually work if the kernel and user driver versions match exactly, all the way down to the patch version of your driver. There is no ABI compatibility between what they install in user space and what they have inside the kernel. And if these even differ by, like I said, a patch version on your driver, things won't work. And so you can't just take your container and assume that you're going to bundle everything up in user space. So our solution to this, and we've had a solution in place all the way since 2016 for this, is to, instead of bundling these user space libraries inside your container, instead you want to inject the ones that have been installed on the host by your NVIDIA GPU driver, inject them at runtime into your container. So you don't bundle these libraries. You assume that once this container lands on your machine, something will kick in to automatically trigger these libraries to become available in the container for you. And then obviously we also have a way to make the GPU devices themselves available. Otherwise, you would have to go through the manual effort of making sure that you list out the GPUs that you want available on the command line manually. And so if any of you have ever interacted with uh, GPUs via Docker, this command on the left should look familiar to you, right? You can do Docker run. You can point it at our own custom wrapper around, it's actually, it used to be a wrapper. Now it's more of a front end in front of run C. But you can point it at the NVIDIA runtime rather than the default run C runtime behind the hood or under the hood. And then you can set this environment variable to tell it a set of GPUs that you want this container to have access to. And behind the scenes, it'll do all the necessary work to inject all the libraries, inject all of the device nodes and everything else that you need to make GPUs 0 and 1 visible and available to the workloads running inside this container. This is obviously a very simple container. I'm just running NVIDIA SMI to print what GPUs are there, but everything has now been injected into this necessary to run more complex CUDA workloads. And the GPU support that we built into Kubernetes also relies on this NVIDIA Container Toolkit stack. So if you have a pod spec and you request a set of GPUs using the extended resource type nvidia.com/GPU, it's using the NVIDIA Container Toolkit behind the scenes to do the same kind of injection. So, this pod will get scheduled on some node. That node will then trigger a component called the GPU device plugin, and when the container goes to actually get started on the machine, magic will happen to make sure that all the libraries and the device nodes get injected into your container properly. So how did we actually reach this point? Where did this extended resource of nvidia.com/GPU2 come from? And what was the evolution from the first support that existed in Kubernetes up until the ability to do this that we have today? If we go back all the way to July of 2016, this was when the first PR was submitted to Kubernetes, which added direct in-tree support for GPUs. There was no notion of a device plugin. There wasn't this kind of extended resource called nvidia.com/GPU. Instead, it was a hard-coded resource similar to what we have for CPU or memory, and it was called alpha.kubernetes.io/NVIDIA GPU. And this initial support only supported a single GPU. So if you asked for anything more than one, your pod wouldn't get scheduled. It didn't work, and there was no support for library injection. So you actually had to bundle your libraries into the container, and you had to make sure that when you scheduled it, it landed on a node that had the exact driver that could run that container with matching the user space libraries that you had bundled into it. And this was contributed by a company called Clarif AI. A few months later, in December of 2016, multi-GPU support was added into this. So instead of just being able to ask for a single GPU, you could now ask for multiple GPUs. It was still via this alpha.kubernetes.io NVIDIA GPU resource type, but now you could at least ask for more than one instead of just a single one. A few months later, in February, support for this feature was taken over by the GKE team at Google. And at the same time, they started collaborating with us at NVIDIA in terms of hardening the implementation, adding proper unit tests, ETE testing around this to make sure that it actually was robust enough to be used in a production setting. And then about 6 months later, in the summer of that year, in collaboration with NVIDIA and the GKE team, we put together the initial device plugin framework for Kubernetes. So it was a generic framework for plugging in any type of devices into Kubernetes, not just NVIDIA GPUs, right? So now using a plugin, you can register an extended resource type, NVIDIA.com GPU in our case, and you can make sure that people can request those and then use the plugin to ensure that the devices that they're asked for are injected into the containers at runtime. In October of 2017, so a few months later, GKE moved completely onto this device plugin framework. So they stopped using the in-tree GPU support completely and instead decided to write their own device plugin instead of using Nvidia's because we didn't have one available yet. And an interesting tidbit is that are still using this today. They're still not quite using the Nvidia uh, standard device plugin for injecting GPUs. They still have their own that they use and maintain. Um, then in February of 2018, so 6 months after that initial release from Google with their device plugin, Nvidia released their first device plugin. It was based on Nvidia Docker and the Nvidia Container Toolkit under the hood, and it stands to be the reference implementation for all future device plugins that were written, right? So it kind of was and still is this reference implementation. So if you've ever written your own device plugin, you've likely looked at the example plugin that's inside the Kubernetes tree itself, and that was the initial plugin that Nvidia wrote to get device plugin functionality working at all inside Kubernetes. And then in March of 2018, so roughly a year and a half after the initial support for GPU was first added in July of 2016, that in-tree GPU implementation was completely removed, and all future efforts since then have been focused exclusively on the device plugin framework and improving the GPU support we have in this environment. And so this is what I kind of categorize as the past. This is how GPU support initially was working in Kubernetes, and we've now moved on to this more advanced device plugin framework, which we've now had around for 6 years, which is quite a lot of time. So before I move on to the present, what does it look like today? What capabilities does Kubernetes provide for using GPUs today? I just want to pause right here real quick and see if there's any questions I can ask or that I can answer up to this point.
So I do see we have one question here that was actually been brought up from one of our viewers right at the beginning. So I think that this is in someone who's super excited and already wanted to ask something, which I love. So Guan Cho, I hope I said it right. He asks, or she asks, when pre-compiled driver containers would be promoted to GA.
Yeah, so this is a very specific question.
It sounds like it.
It's not, yeah, it's not something I was planning on touching on in this conversation. This is more about timelines for actually releasing of the software that we're developing here. Um, and I don't have a good answer for that. Our product managers would know more about exactly when this is going to be released to GA. I know we do have precompiled drivers. We do ship those, and they're the default now for many environments with the GPU operator, which I'll talk about a little bit later on. But I can't comment exactly on when they'll be going GA versus the state that they're currently in, unfortunately.
I would like to ask, what did the device plugin framework enable? Like, why was it important? Maybe you talked about it and I missed it, but I would like to hear a little bit more about it.
Sure. Yeah. So, as you can imagine, hard coding a specific resource type into, Kubernetes itself meant that the only way you could add new functionality or new features to it were to open up PRs directly against Kubernetes and change the implementation there. Which in theory isn't too terrible, but it meant that third-party um, developers of different devices would all have to do the same as well going forward, right? So when it was in tree, it was a specific type, just like CPU and memory, that you had to, that you had to kind of get consensus on. You had to agree upon that this is something that we want to add to the actual Kubernetes API as a concrete resource type that people are able to request access to. And with the device plugin framework, you don't have to do that anymore, right? Dynamically, plugins can register their types, and any features that you want to continue to add over time for what devices those are, how you make use of them, those can be developed independently in these third-party plugins rather than having to develop it directly against Kubernetes itself. And you don't have to get buy-in that this is, yes, a new built-in resource type we want to make available. All of that can be, it can be added as part of the Kubernetes API extensions rather than something built into Kubernetes itself.
Right. Yeah, that makes sense. Like, I figured that it's probably, the usually when you go to the direction of why do we need a framework, well, it's mostly around, okay, so everyone can reuse something, or to enable more flexibility. But I was interested in particularly for this use case, and thank you for
Mhm.
answering that. I think let's move on, and if there will be any more questions, then we can
Sure.
we can answer them
Yeah.
in our next Q&A stopping point.
I'll
So
pause again at the present before we
yeah,
move on to it. So if anyone
which is
wants
an
to queue up
interesting.
their questions now, they can. Yeah.
Yeah, so I highly encourage everyone watching us to ask more questions. Yeah, don't let me take all of his time by myself, really. But I can, like, I'll happily do that. So, yeah, we're listening. We're with
Okay.
you. Let's jump to the present.
Okay. So once this initial support for the device plugin was in place, um, we added a couple more components to the ecosystem. So it's not just enough to be able to advertise GPUs and make them available to Kubernetes. We also want to be able to do things like gather metrics about those GPUs. And so in May of 2018, we released a component called the DCGM exporter, which is a Prometheus exporter to gather GPU metrics and make them available in a GUI like Grafana or any other front end that you can put in front of Prometheus. And it runs as a standalone pod next to the device plugin rather than as part of it. Um, After that, we added a component called GPU feature discovery, which is able to advertise um, the capabilities of the different GPUs that exist on an individual node in your cluster as node labels, which now enabled people to um, direct workloads to nodes that had the type of GPUs that they cared about. So before this point, if you asked for a GPU and your cluster happened to have a mix of different GPU types on different nodes, there was no guarantee as to which GPU type you were going to get. You were going to land on some node that happened to be advertising GPUs. But with the introduction of these labels, you could now use node selectors to direct your workload to a specific GPU type, if that matters for the workload that you're trying to run. Um, and then in February 2020, we released a component called the Nvidia GPU operator. So the question that was asked before was very specific to something, the driver containers that we ship with this component. But the power of the NVIDIA GPU operator is that it takes all of the components that are necessary to run GPUs, um, to make use of GPUs within Kubernetes on an individual node, and it installs the entire software stack. It automates the process of installing that entire software stack on a node as it first comes online and connects itself to Kubernetes. So as long as your node has GPUs installed and you have a component running on it called node feature discovery, which will allow our GPU operator to discover that GPUs are there, it will then take over and install everything else on the node that's needed to eventually make those GPUs advertised by that node and consumable by workloads that get scheduled on it. So before I go on to a little bit more about the history here, I want to just kind of jump in and deep dive on what the GPU operator itself is real quick. And as I mentioned, it automates the installation of the software stack needed to make GPUs available in Kubernetes, where the components that it installs can be broken into two categories. There's sort of host level components. So things that need to be installed directly on the host. They don't run as daemon sets. They don't run as standard Kubernetes primitives within your cluster. They get installed directly on the host operating system itself. And then instead of standard Kubernetes components like the device plugin that I've been talking about, the GPU feature discovery component, and the DCGM exporter. It bundles all of these things together and makes sure that they, come up and get installed on your node. And once everything's running, workloads can actually get directed to these nodes and consume the GPUs there. Um, just like what you see here, right? So this is just an example. I showed this before, but I'll just show it again. That if you put together a pod spec like this, assuming the operator has discovered these nodes, installed the software stack on them, you ask for nvidia.com/GPU2, your workload's going to get scheduled to one of these two nodes, and you're going to get two GPUs that are available on it. Now, as I mentioned, without something like GPU feature discovery, there's no guarantee whether you're going to land on the node on the left, which has V100 GPUs on it, or the node on the right, which has A100 GPUs, which are obviously much more powerful. Um, and so what you can do is with the GPU feature discovery available and advertising node labels, you can use a node selector to say, hey, you know what? I want 2 GPUs, but I want to make sure that that they land on a node that has A100 GPUs rather than B100 GPUs. So you can, more successfully get access to the GPUs that you're looking for. And then as well with the DCGM exporter, as I mentioned, you can export metrics and then use something like Grafana to display those metrics and get insights into how the GPUs on your nodes are performing. Okay, so that was back in February 2020. So over 4.5 years ago now, since this initial release of the operator. Over time, we've added a lot more features to the operator, as you can imagine. For the purpose of this talk, I'm just going to focus on a few, and specifically ones that that we've added over the last few years to enable different types of GPU sharing. So, traditionally in Kubernetes, if you ask for a resource, it's assumed that you get exclusive access to that resource, right? So if you ask for a GPU, it gets given to you. No other pods are going to be able to access that GPU, right? But because GPUs are expensive and sometimes applications don't need the full power of an entire GPU, we've added different capabilities over time to allow users to share access to GPUs in a more controlled way. And the three methods that have been added over time are a method of doing hardware partitioning with a technology called MIG, allowing GPUs to be shared to be time sliced amongst different clients that connect to them, as well as a software partitioning mechanism called MPS. And I'll talk about these three. I'll deep dive into these three a little bit right now. So as I mentioned, MIG is a method of hardware partitioning a full GPU into a fixed set of what you can think of as kind of mini GPUs. And what's nice about this being a hardware technique rather than a software technique is that you actually get full isolation between workloads running on different MIG devices. This is suitable for multi-tenant environments, whereas a software solution wouldn't really be, because if something goes wrong on one of your GPUs in a software partitioning setup, it could take down the other GPUs, which you obviously don't want if you're running in a multi-tenant environment. And to get access to this type of sharing, there's a new extended resource type that we advertise for these different MIG devices. So when you slice up a GPU into a bunch of MIG devices, there's a canonical naming convention that goes along with that for how you reference one of these MIG devices and get access to it. And we've encoded that into the extended resource type that gets advertised by Kubernetes. So if instead of getting access to a full GPU, you actually want access to one of these smaller MIG devices, you won't ask for nvidia.com/GPU. You'll instead ask for nvidia.com/MIG, and then you say what size MIG device you want access to. And so I'm not going to go into the details about how this naming convention came to be and exactly what these different fields mean, but suffice it to say that this is asking for a MIG device that has 5 gigabytes of GPU memory available. Is essentially what you would translate this to. Okay, so if that's hardware partitioning with MIG, we've also added the ability to do time slicing. So this is a simple oversubscription of multiple workloads on top of a GPU, and it's managed by the CUDA runtime behind the scenes. And so what this will basically do is if you have two different pods that are referencing the same GPU, they'll have access to the full memory that's on the GPU. They'll have access to the full set of SMs, which is the compute side of things on the GPU. And so during its time slice, it gets access to the full GPU and can do everything that you would normally expect it to be able to do with that full GPU. But it's being time sliced with other clients that happen to be attaching to it as well. So if you have a latency sensitive application, you wouldn't want to be using time slicing because you have no guarantee about exactly when you're going to be running. But if you're not as sensitive to latency, it might make sense for you to do some time slicing with other clients because it lets you get more use out of the GPU than if you only had it dedicated to one job that's running and it wasn't able to use it all of the time. And the way this is enabled in Kubernetes is through a config file against the K8s device plugin itself. And so if you look on the right here, I'm showing how an admin would set up and enable time slicing for use within the cluster. They would on a per node basis, you can point it at a config file that says that for the nvidia.com/GPU resource type, I want each of the resources that are available to have 3 replicas being advertised by them. So imagine you're on an 8 GPU machine. You configure that machine with this configuration. From the Kubernetes perspective, it's now advertising 24 GPUs rather than just 8, because each of those individual GPUs is advertised as 3 replicas, and now 3 different clients could be time sliced on top of each one of those GPUs, depending on when and how they were attached to it. And the syntax for then asking for that in the pod spec is via an extension to the nvidia.com/GPU resource type of dot shared. So when you put dot shared there and the node has been configured like this, you're going to be sharing this GPU potentially in time with other clients that are attached to it. And you can do this with MIG devices as well. It's not limited just to full GPUs. You can also configure it such that different clients can be time sliced on top of the MIG device in addition to full GPUs. So you can first hardware partition these MIG devices and then time slice on top of those. And the last technique is something called NPS, which is a software solution for dividing up GPUs, similar to what we had for MIG, but in a much more fine-grained way. So with MIG, there's only a very specific size of the different mini GPUs that you can create. But with NPS, you can create arbitrarily sized partitions. So you can decide yourself how big of a memory partition to give it, how much fraction of the compute I want to give it, and you can control this in a much more fine-grained way, which is why you might want to do this over something like MIG or on older GPUs that don't support MIG, because MIG is a feature that's only available on Ampere GPUs and beyond. But it's very similar to MIG logically. It's a space partitioning method rather than a time partitioning method. And just like with time slicing, the user interface from the pod spec perspective is identical, except that on the node, instead of configuring it for time slicing, you're configuring it for NPS. And now when multiple GPUs get shared by different clients, they're not going to be being shared in time. They're going to be being shared in space by whatever configuration parameters that we've set up for this. And so the way that the replicas work here, it's not oversubscribing the GPUs. It's instead saying, okay, if I have a 30 gigabyte GPU card and 3 replicas, each one of the clients that connects to this is going to get 10 gigabytes because there's 3 replicas, 30 gigabytes divided by 3, and you each get 1/3 access to 1/3 of the GPU. And so this is obviously more appropriate to latency sensitive applications than the time slicing sharing method, because you have full dedicated access to some small portion of the GPU, but you're limited on how much memory you have available to run your workload with. You don't have access to the full memory, you only have access to the 1/3 of the memory that's available there and 1/3 of the compute. And again, this can be layered on top of MIG. So instead of just asking for MIG 1G 5GB shared, or 1G 5GB, you can say add the dot shared extension, and it will make sure that you're space partitioning that MIG device rather than the full GPU. Yeah, and so that's kind of where we are today. But what does the future look like? So again, I'm going to pause here, and it seems like there's actually, I'll go one more slide. I won't go through these yet, but just to point out that even though this seems like there's quite a bit that we can do with what we have today, there are a number of limitations. And so after the questions, I'll go through these limitations here, and we can talk about how we're addressing these going forward.
So I do want to say that I'm writing down as you talk, because I wanted to write like a few questions that I have, and one of the questions I was like, what are the limitations? And then you were like, just one more slide, and then this slide came along, which is that's always perfect. So I guess I won't steal all the time, because I do see that we have a few questions, but I kind of want to ask mine first, and then I'll go for the viewers' questions. You forgive me, right? Come on. So just a quick question, really. Are there any like good practices or like something that you'd say, okay, this is somewhere that you can read about it more in order to navigate through? Because I do feel that sometimes with configurations, I found myself a lot getting to the right values in, in a more trial and error sense. So I guess that in cases like this, they might not be some very, like, a lot of good practices, but if there are, um, what are they, or where can we find
Yeah,
them?
sure. So I tried to to quickly say, like, okay, what type of application might you want to use this sharing technique versus this other one versus this other one. And we did write a blog post a few years ago that goes into a bit more detail about this, and I can send it to you guys after the presentation. And I'm not going to read out the URL right now, but I can, send it after the presentation. You can share it with the viewers.
Yes.
But in general, the best source of information for how to do these configurations and what the advantages and disadvantages of them are is the you know the official NVIDIA documentation on the GPU operator. So the GPU
Mhm.
operator has, you know a very detailed documentation site on all the different knobs that you can turn and what you can enable and what you can disable. There's obviously some things that are missing. There's some, I wouldn't call them hidden features, but they're just more undocumented because we haven't gotten around to documenting them over time. But all of these different sharing techniques are documented pretty extensively. And so if you're interested in trying some of these out, and you are using the GPU operator, yeah, the official documentation for the operator is the best place to go for that.
Okay, that's very cool. And also, you know what?
And
I'm
sorry,
gonna
one
hold.
last thing
Yes, please.
I'll add there too is that all of this stuff has been talked extensively at various KubeCons. And so if you go back through different talks that have been given by NVIDIA at KubeCons ever since 2018, those give kind of more deep dive technical descriptions of how all this stuff works under the hood than what I'm doing today. I'm giving a much higher level description.
And I do think that it's important work that Nvidia is doing. Obviously, companies, it's a business, they want to advertise, but also I do feel that watching these deep dive talks, it really helps the users to better understand what is the source of things, why are things are being done the way that they are, and then it helps us to better understand how to do everything, and what's better than other things. Okay, I'm going to stop my questions now, and I will ask some of the questions that I see here. And please forgive me, everyone, that I'm not asking all of the questions that I see here. We don't have a lot of time, so I'm just going to pick whatever I see coming up, and yeah. So I think I'll take like 2 or 3 questions, and then we'll move on if that works.
Mm-hmm.
So. I see that there is one question. Is there a way to automate the host level component deployment using another operator? Or should I use the image/post installation scripts?
So with the GPU operator, you can either pre-install the host level components yourself, which I think is what your second part of your question is saying,
Mm.
um, or you can have them be operator managed. And so, when I said that that they're installed directly on the host, they are done so via containers. So we do start up what's called a driver container, and it's kind of a misnomer because it makes it sound like we're running the driver within the container. But what it's actually doing is it's a container that comes up and triggers the installation of the driver into your kernel, and then any user space components end up in the file system of that driver container. And then we have methods to export that back out into the host, and then make other components aware of it so that everything can be stitched together properly to eventually make the GPUs available to you. Um, so when you talk about automating the host level components, um, there are methods such that the GPU operator will just do that for you. Or if you want to do them manually, we do have a component called the CNS. It's the Cloud Native Stack. If you go to github.com/NVIDIA Cloud Native Stack, um, it can automate the process of bringing up a Kubernetes deployment to begin with. So, the low level infrastructure, bring Kubernetes online itself and get these components installed for you with the latest drivers and the latest components if you don't want that to be managed by the operator yourself. So we do have, and then you can turn on and off what you want to do. If you already have a Kubernetes cluster, it'll automate just the installation of the host level components, or um, if you don't have your Kubernetes cluster set up yet, it will do that for you as well. And you can fine tune what you want it to install and what you don't. And it's all Ansible based. So yeah, so I hope that answers the question.
To me, it
Yeah.
did. So, and again, if people want to ask more on that, then oh yeah. So okay, so the person who asked says, "Perfect, thank you. The operator sounds good enough." Yeah, same to me. Let's take just one more question. We have: is there a possibility to prefer allocation of GPUs and CPUs on the same NUMA node?
Yes. So back in 2018, 2019, there was a component added to Kubernetes called the topology manager. I actually wrote the topology manager, so I know how it works kind of inside and out.
So it's a
And
good
yes,
question.
that's a good question. Yeah. Um, we you can make sure that CPUs and GPUs are aligned by the same NUMA node if you enable the topology manager in your Kubernetes deployment. So it's a flag on the kubelet. You enable topology manager, and basically behind the scenes, what happens is that the CPU manager um, kicks in to make sure that any CPUs that you get access to are from a specific NUMA node. And the GPU device plugin is also advertising what NUMA nodes those GPUs are available on. And inside the kubelet itself, it'll do this alignment. So it'll make sure that any CPUs you ask for and any GPUs you ask for will get aligned before they get granted to your application. But you have to enable this special feature flag in Kubernetes for the topology manager to make this work. You have to set up a specific policy for it. Um, um, yeah, and this is actually so that's how you do it today. So maybe
Yeah,
this is a good segue into what I'm
that's
about
a
to
good
talk about.
segue to our next.
There's a better way. There's a better way to do it in some of the new stuff that we're adding to Kubernetes to address some of the other limitations.
Let's jump on that segue and move along.
Okay, yeah. So as I mentioned, with the existing support that we have today, there's quite a few limitations with what's there. One of the big ones is there's no support for having more than one GPU type per node, right? I mentioned that that there was the ability to use GPU feature discovery to direct workloads at a node that has a specific type of GPU, but that implies that that node has a homogeneous set of GPUs on that node, right? If you had a V100 and an A100 on the same node, just using a node selector isn't enough to get you access to the GPU you want, because it's just a label that's applied on the node, not a label that's applied to the device itself. There's also no support for providing complex constraints when requesting a GPU. The only knob we have is a number, right? If you want access to, if you want to say what type of GPU you want, you can't really say nvidia.com/GPU and you say how many, but there's no way to constrain that any further, at least not with your actual request itself. There's also no control over how oversubscribed GPUs are shared between jobs. So I talked about this whole time slicing method that we have for sharing GPUs, but you as the end user can't control which two of your jobs happen to run on top of the same GPU, right? The kubelet is in charge of handing these out, and yeah, you oversubscribe them, but you can't say that this application's sharing it with this one and this other application's sharing, you know, the GPU with a different one. You can't control how that's done. And the same is true for MPS, right? So you're space partitioning this GPU. You can't make sure that two applications are running side by side on the same GPU, at least not with the support that exists today. There's also no ability to dynamically provision MIG devices based on incoming requests. So I showed that you can, request access to MIG devices, but it's actually contingent on the fact that you have an admin that has decided, okay, this node in my cluster is going to advertise these specific MIG devices. So I'm going to take a set of GPUs, I'm going to slice them up. That is now a static configuration this node has, and those MIG devices get advertised, and now you come in as a user and you request access to them. What would be nicer is if a GPU could either be used as a full GPU or repurposed into advertising a set of MIG devices in whatever arbitrary size you want, dynamically based on the workloads that are actually coming in, right? And that's not possible with the support that we have today. And then this last one actually is um, relevant to the question that we just had about the ability to align different devices. So yes, you can align on NUMA node, but that's the only thing that you can align on with the topology manager. And some of the new support that we're adding to Kubernetes will allow us to align on arbitrary attributes of different devices, whether it's the NUMA node that they happen to exist on, whether it's a common PCI root complex. It can actually be anything that you want to be able to align on. You as a vendor writing your plugin for this new method that I'm about to describe can decide yourself what you want these um, um, attributes to be that you will align on. NUMA node, PCI root complex, whatever. And I'll actually show an example of this at the end of the talk. Okay, yeah. So the feature, the big feature that's being added to upstream Kubernetes itself to enable all of this is this feature called dynamic resource allocation, and it addresses all the limitations that I just described and more. And so, I'll talk about kind of what the user-facing API for this looks like. I'll talk about the history of it a little bit, um, and then but I'll leave it as an exercise to you guys to research this a bit more if you're interested in it and see what things this actually enables that you've never been able to do before, independent of GPUs, right? GPUs have been the motivating example for adding this to Kubernetes, but it's not the only use case. So I encourage you to kind of think to yourself about where else this could be used beyond GPUs as I go through this. Right. So dynamic resource allocation itself it's a new way of requesting resources that's been available as an alpha feature in Kubernetes since 126. It's actually changed quite a bit since then. So, um, I've given presentations at KubeCons in the past where I say this is the most amazing thing we've ever done in Kubernetes. Everyone get really excited about this. Here's how it works. None of that is relevant anymore. It's all changed in the most recent version of Kubernetes. The things you can do with it still exist, but the way that it's done is very different. And so, what I'm about to talk about now is actually the source of truth for what it looks like in the newest version of Kubernetes, different than what I've talked about it in the past if you've watched other talks that I've given before on this topic. And in general, it provides an alternative to the count-based interface of asking for, nvidia.com/GPU2, which is a much richer interface um, that was inspired by the persistent volume API. So if you're familiar with the persistent volume API, you can separate your declaration of what you want access to from where you actually consume it. And so this enables things like GPU sharing in a much more natural way than what we could have done before. And it uses the technology called CDI under the hood to do its device injection. So I didn't talk much about CDI, but it's another CNCF sponsored project that is being worked on by my team at Nvidia, and it kind of underpins how all of the devices themselves make their way into a container in Kubernetes using the mechanisms of DRA. And the key concepts behind this are that of what's called a device class and then a resource claim, which again, if you're familiar with persistent volumes, these things shouldn't be too foreign to you. So before I go into what the user-facing API looks like for this, it's somewhat important to kind of get a picture of what one of the drivers for this new DRA mechanism look like. And so, in general, just like the device plugin, you have, the way the device plugin worked in the past is, you install it on a node, it looks at the node, says, okay, what devices are available, and then it advertises those to the kubelet to be able to allow pods to request access to them, right? And in DRA, you have a similar concept. You have this what we call a driver rather than a plugin, a driver running on any individual node. You can imagine deploying it as a daemon set on all the nodes in your cluster that have GPUs. They're looking onto the nodes, figuring out what GPUs are there, and then advertising this new abstraction in Kubernetes called a resource slice, so that the Kubernetes scheduler can eventually consume these resource slices, see what resources are there, and then allow your pod to request access to them, right? And so in the example that I'm showing here, I'm saying, okay, we've got a resource slice. It's associated with my gpu.nvidia.com resource driver that we've written. And then in this example, I'm just listing one single GPU. So devices themselves, become a named list of attributes and capacities, basically. And so, as I mentioned, there's one GPU here. I've given it a name GPU0, and then attached to that, I'm putting a bunch of attributes. Here I'm showing that I've got a UUID of this long string. This GPU exists at index 0 on my machine. It's an Nvidia GH200 with 96 gigabytes of memory. And the driver that's running on this machine that governs this GPU is version number 550.94.0, right? And then there's a set of capacities associated with it. And so I'm highlighting here that there's 96 gigabytes of memory, but we might have other capacities that also exist to describe what this GPU looks like. And with this in place, you can have a device class, which is defined as follows. And so in the GPU driver that I've written for DRA, um, um, uh, we install this device class for you in your cluster. So you do a home install of our GPU DRA driver, and this device class becomes available for you as a user to consume and make use of. And the only thing this device class is doing is giving it a name, gpu.nvidia.com, and then telling it that if you reference this device class, I want to allocate a resource from the driver whose name is gpu.nvidia.com. So as I mentioned, my driver is going to enumerate a bunch of resources via these resource slices. These resource slices are associated with a driver. And now this is just saying that it's basically informing the scheduler. If someone references this device class, make sure you pull a GPU from a resource slice that's governed by this driver, right? And so, you can list out a bunch of GPUs, and then the scheduler will make sure to pull GPUs from that list when you request them. So what does it look like to actually request them, right? So if that's what a device class was, here's how you actually make use of this inside of a pod spec. So you first need to create a separate object called a resource claim. We eventually hope to fold this into the pod spec itself so that you don't have to actually create a separate object yourself. But because this is still an alpha feature, and even through beta, it'll probably exist as a separate object. But the idea is that we eventually want this to be part of the pod spec itself so that you don't have to, manage the life cycle of these external objects. But for the purpose of now, in 131 and even into 132, Kubernetes, it's going to look like this, where you create a resource claim. In this example, I'm giving it the name shared GPU. I'm telling it that I want to request a device associated with the device class of gpu.nvidia.com. That has now fully defined my resource claim, to which the scheduler will eventually bind some GPU. And then in my pod spec, there's a new section called resource claims. I point it at the name of the resource claim that I created. I give it a local name called GPU, and then I reference that in two different containers. And because by construction, the way this all fits together, I now have done controlled time sliced GPU sharing amongst these two GPUs. So I know that container 0 and container 1 in this pod are the only ones that will have access to this GPU. And because I didn't mention this, but we enable time slicing of GPUs by default in these environments, this will force these two GPUs to be, time sliced rather than shared by some other mechanism. And again, if you're familiar with volume mounts and persistent volumes, this should look very familiar, right? This is similar to a section called volumes, where you declare what you want access to, and then you can reference it inside different containers to get access to it. This extends beyond just a single pod. You can now share GPUs across pods if you want. I've got this top level object called a resource claim. My two different pods reference that shared GPU claim, and now I've controlled which two containers in which two pods I want to share access to this GPU, right? And I don't show it in this example, but resource claims are namespace objects. So you can only reference a resource claim within a specific namespace to make sure that, some other user on your system isn't able to access GPUs from resource claims that users in a different namespace have created, right? So again, I showed this before. This is what a device class looks like. It's saying I want to select any device governed by the NVIDIA DRA driver for GPUs. And I also showed a resource claim that can access that, but there's also a bunch of other fields that you can add to these resource claims to configure the GPUs behind the scenes once you've been given access to them, right? So it's this notion of selection versus configuration, right? What I showed before is how do you select a GPU, but then there's also the ability to instruct the DRA driver to configure it in a certain way once you've been given access to it. And so in the example I'm showing here, I'm showing how you would say, okay, you know, I'm going to create a resource claim. I'm going to request access to a single GPU, and when you give me that GPU, make sure and configure it with MPS sharing strategy enabled, where every instance that connects to it is going to be given 10 gigabytes of that GPU and 20% of the compute resources that are available on it. And this is just an example. We've got a bunch of other configurations that you can define for this, but it lets you as the user decide yourself, when I get access to the GPU, how is it going to be set up for sharing in a fine-grained way amongst the different clients that I give access to it. And for a more complex example, in terms of doing alignment, we talked about NUMA nodes being aligned, but that's not the only thing you can align with. This is meant to demonstrate how you might put something like this, something more sophisticated together. So in this example, I'm saying, I have a single resource claim that's saying, give me a GPU from the gpu.nvidia.com resource class. And then you use this syntax called cell to basically say, when you give me that, make sure that the memory for the device that you give me is at least 80 gigabytes. So I don't want any GPUs with less than 80 gigabytes of memory available on it. At the same time, I also want access to a NIC, which is going to be pulled from a different GPU or a different driver. It's not even the gpu.nvidia.com driver. It's the RDMA nvidia.com driver. And when you give me access to that NIC, I want it to be a virtual function from the SRIOV interfaces that are being exposed by it. And when you give me those, make sure that they're aligned such that the GPU that I'm given and the NIC from which this virtual function comes are aligned on the same PCIe route behind the scenes. And so, I showed that resource slice at the beginning of how these different attributes and how the different, capacities are being advertised. These are attributes that are being advertised by these two different drivers about the resources that they have. And so the schedule will make sure that when it's finding a GPU and it's finding a NIC to give you, it'll make sure that they're being pulled from the resource slices such that they both have an attribute called kh.io PCIe root that has the same value. So it kind of joins these devices by the values that you put in these match attributes. And for a more concrete example, which I actually have in my GPU driver that I put together today, is if you want to do something like aligning two MIG devices to make sure that they're allocated on the same underlying GPU, right? Because otherwise you ask for a MIG device, who knows exactly which GPU this is going to come from. But using this mechanism, I can say, give me access to a MIG 3G 20GB device and give me access to a second MIG 3G 20GB device. But make sure that those come from the exact same parent GPU when they get sliced up from it. Because I will have advertised via my resource slice associated with these MIG devices what their parent UUID is, so it can match on that common property to make sure that they get aligned from or get allocated from the same one. Right, so that's kind of DRA in a nutshell. There's a whole bunch of use cases that it enables. I only really focused on the sharing mechanisms here and a little bit of the alignment. But we first introduced kind of the more modern version of DRA. Like I said, it's been available since 126, but we've changed the API that it has quite a bit over the last few releases. And the one that we introduced in 130 is pretty similar to what we now have in the newest version of 131. And it was able to, I wrote this document called NVIDIA GPU use cases for dynamic resource allocation. And the APIs that we had in 130 were able to cover 6 of those 12 use cases. About half of the things that we wanted to be able to do with DRA that we couldn't do with the existing device plugin. In 131, we expanded that to cover 2 more of the use cases, so 8 out of 12. And by 132, we actually plan to support all but one of the use cases that we have, where that last one will most likely never be supported directly by DRA. Because if you read it at the bottom there, it's about having very application-specific policies for how you allocate GPUs across different containers and pods. So it's really hard to come up with a generic framework such that the built-in Kubernetes scheduler can do something that's very application specific in terms of allocating these things, right? In what we call classic DRA, which is what we introduced back in 126, something like this was possible, which is why it's even listed as something that we would like to be able to do. Um, but if we want to have something built into Kubernetes itself, which is the way that the community's pushing this feature going forward, we'll probably never actually be able to support these application-specific policies, at least not in the way that we initially envisioned with the support we had in what we now call classic DRA. There's been a bunch of talks on DRA at various KubeCons. There's actually a few talks on DRA coming into the KubeCon in Salt Lake City in November. So if you're going to be there, I encourage you to come to the talks. Nvidia, for the first time since 2018, will actually have a booth at KubeCon this year. I plan on spending most of my time there when I'm not attending sessions. So if you want to come meet me in person, ask me any questions about what we've talked about today or anything else about GPUs, I look forward to seeing you there. Um, and yeah, the most relevant one for what we've talked about today is this one from KubeCon last year in Chicago, where I first kind of introduced how all this DRA stuff is really going to unlock the full potential of GPUs for AI workloads on Kubernetes. So I talked about some of the things I talked about today in this talk. But as I mentioned, all of the APIs and the details about how I say, oh, you're able to do this, and this is what the APIs look like and all of that has changed. Nothing is the same. But what I talked about today is the new way of that going forward, and then obviously there'll be documentation on what the future holds once this moves into beta and eventually into GA going forward. If you're interested in tracking the latest developments with DRA, the source of truth for the feature itself is always the Kubernetes enhancement proposal. It's a long URL here, but we'll share the slides afterwards so that you guys can click through these and review them yourself. There's also a working group in Kubernetes called the Device Allocation Working Group. It's an active working group. Its charter is basically to do everything that's necessary at the lower levels of Kubernetes to enable advanced use cases for AI and accelerated workloads in general. Its first charter is to bring DRA to GA in the next few releases, but I assume it will exist. It'll continue to exist beyond DRA eventually becoming a feature, and we'll just continue to add new things that are relevant to enabling these types of the workloads going forward. There's also an example DRA driver that I wrote under the Kubernetes SIG org on GitHub. You don't need GPUs to run this. It's more just a demo of, so it's got simulated GPUs, if you want to call that. It's, it fakes, it doesn't run workloads on GPUs, but it pretends that there's workloads that GPUs that you can allocate to your system. It runs inside a kind cluster. And so if you want to just, download this, see what DRA has to offer, how it works, you can run it on your Mac without GPUs. You can run it on Linux. You can run it wherever that kind will run, and you can get a feel for DRA. There's also a DRA driver for networking that Antonio from Google put together. So, I tend to always focus on GPUs, but GPUs isn't the only use case for DRA. It's also relevant for networking and other types of devices. And then, there's obviously the Nvidia's official DRA driver for GPUs, which, is still actively under development. Things are still changing in Kubernetes itself. We plan to eventually make this production ready by the time DRA upstream does go GA. Actually, in fact, by the time DRA upstream goes beta, which we're hoping will be in 132, we'll also release this for people to use and run in production. So yeah, reach out if you have any use cases where you think DRA could help, and happy to answer any questions about any of this going forward. Yep, that's it.
All right. First of all, thank you so much for all of this wonderful information. I've written so many things here that I think it would make more sense for me to ask you in Salt Lake, because I'm also going to be a speaker there this year. Great. So I'll see you there in KubeCon. But so before we wrap up, I think that I'm going to take one of the questions that I see over here, which I find to be very interesting. Ethan Patel asked, do I need to use enterprise GPU to use it in a pod or a deployment. And then he also mentioned that that GPUs, enterprise GPUs, they can get very pricey. So
Mhm.
yeah, that's an interesting question, actually. Um, I guess not only for production, maybe also for testing, let's say. But you did mention that example that you have, that people can test
Yeah.
the array specifically on their machines. But I think that this question is very interesting.
Yeah, no, it's not specific to data center or enterprise GPUs. So, we do actually do a lot of our testing on Jetson Nanos, just as kind of a smoke test to make sure that, you know, everything works, everything comes up, everything runs, everything's discovered properly. And so, yeah, no, it's not specifically for enterprise GPUs at all. It doesn't work with graphics only GPUs, but anything that can run you know, I forget the actual, it's a compute rather than a graphics workload, then this is
Mhm.
relevant to those GPUs.
Yeah. Oh, okay, that's fair. So it allows for a more flexible price range, I guess, for
Mhm.
people who maybe want to just try it out, or they're just starting out their journey, running things on Kubernetes, or Kubernetes with GPUs. So that's
Yeah.
a good
And if it doesn't
answer.
work for some reason, I want to know because it should.
Yeah. Yeah, I that was you keep doing that, yeah, Kevin. Like that was my next question. Like, would it be cool if somebody would reach out to you and tell you, hey, it doesn't work for this GPU? Maybe not you personally, but that Slack workspace that you mentioned. So you
Mhm.
already said yes, I think.
Yeah,
Okay.
always happy to help. Mhm.
And all right, so I do want to say, yeah, cool, Ethan. Yeah, Ethan says, "Oh, that's awesome, thank you." And I want to say that too. That's awesome, and thank you. And with that, I think that's a good time to say goodbye to everyone. And we will post the links to the things that Kevin referred to during this session. Would it also be okay if we post your slides, or is there or
Mhm.
and
Yep.
okay, so yeah, because some of the people here asked about it in the DMs, so that's why I asked. So yes, you will also have links to the slides, and that's it. I hope everyone will have a great day, night, whatever time zone that you're in. Have a good one, everyone, and thank you again, Kevin, for sharing your knowledge with us.
Thanks for having me.
Bye bye, everyone.
Bye-bye.